let's just get started in case it takes a long time to go through some of the stuff on this homework. So it's week 5. We're halfway done. Like I just said, the homework should be graded. And I don't know where you have to click it. I think if you go to where you submitted it, it should have some comments or where I did the point breakdown of all that. So that should be up there. One thing I want to point out is that anytime you make a plot for the homework, you should put it in the assignment, because that's usually, you get points for that. So I know some people missed out on a couple points because of that, but I tried to go easy on you if you did that, so I didn't take off too much for it. The problem is, if I can't see what your plot is and you did it wrong, I can't give you partial credit for, if you told the correct answer based on an incorrect plot, then I have to mark it all wrong. So just put the plots in there. Okay, so today, if you guys want, we can go through the UPGMA algorithm. I'm seeing some nods already. So let's just do that, and then you guys can ask other questions based on the homework, all right? Cool. Did you see the video I sent out on Friday? Okay, so that worked. So this is the slide straight to class. And the real meat of what this algorithm is just in this slide, even though it was really brief during the lecture. But the first thing it says is create an initial list, and then it says each sequence is a separate cluster. So that's just already been done when we're given the matrix. So step 1 is generate the matrix, but that's already given up to us. So the next part is just what you have to do for the homework. So it says, while not all clusters are joined, which none of them are joined because you just started with the matrix, it says compute the distance for all pairs, which is already done in the first step, but you have to update it every step. And then you choose the closest pair, or if there's multiple closest pairs, just pick one. And then you join that cluster, and then update all the nodes based on the midpoint. So that's the English version of just what I sent out in the video, and I'll go through it step by step here too. But it's pick a node, merge the node, and then update your table at each step. So that sounds easy, but it's confusing when you get down to it. So one thing I want to point out too is that when we were given these matrices, we only kind of gave you everything above the top diagonal. So the reason we didn't include the diagonal is because if you do a sequence, how similar it is to itself, it's always going to be exactly similar to itself. So it's not going to be useful merging something with itself because it already is itself. So immediately, the diagonal isn't relevant in these calculations. So if you're looking at the smallest number on this table, it has to be smaller or greater than 0, but still the smallest number. And then if you look at the below the diagonal, that's really just a reflection of above the diagonal. So just to kind of remove some more redundant information, anything below the diagonal in the homework wasn't included either. So it might have looked a little confusing where the only thing you were given is A and B as your first pair, and it didn't look like the labels might have matched up or anything. But so this is the full matrix of what's going on in this table, but we only care about the stuff in green, the stuff above the diagonal. So that's why it was given out the way it was in the homework in the slides. So like I say here, the green and the gray are just kind of the same information. Because if you look at the difference between A and B, it's 10. But if you look at the difference between B and A, it's also 10. Okay, so that's simple matrix stuff. But really, we can just only focus on this, just to make it easy. So this is how it's represented in the homework. Okay. So the first step of this UPGMA algorithm is to just pick the smallest pair on the whole matrix. But already we see a problem because there's 2 shortest distances. There's the distance between B and C is 4, but also the distance between B and D is also 4. So in this case, we just pick one. And I say we can pick B and C, so that's what I'm going to do in the slides. If you want to be consistent, you can do it kind of like alphabetically. So C is smaller than D in the alphabet, but you can pick it at random and they're both technically correct for this algorithm. Okay, so I say we select the pair BC, and now we're going to merge them into one bigger cluster. So what does that look like? Right off the bat, can you guys see this on this side of the room? Okay. We make the cluster BC, which is the midpoint between B and C. And if they're 4 away from each other, then the midpoint is 2 away from each other. So the midpoint is 2 away from B and 2 away from C. So these are the most recent common ancestor of B and C is 2 distances away from either one. So that's the midpoint. And it looks easy with 2, but it gets a little more confusing with more. So we'll go through it. All right, so like I said, merge the pair, find the distances, which is just half of the distance between the pair, and put it in the tree. So any questions with this before we start doing more? Because it's only going to keep stacking on top of this. This is pretty good. You found a pair, and then the midpoint between the pair is just the pair divided by 2. Okay, so now we have to update the table. So how I'm going to show these slides is always on the left is going to be the original matrix. In the middle is going to be like our current state of the matrix. And then the tree is always going to be on the right of this line. So because we merged B and C, we have to compute the distance now between A and B and C, and then B and C between the other rest of the pairs. But one thing I want to point out is you already still know the distance between A and B and A and E, so we don't have to update these numbers on the table. The only numbers we have to update is anything that concerns the pair that we just merged together into a cluster. So with that in mind, there's 3 numbers we have to get now in this updated table. And we merged columns B and C just into one BC column. So this is like the current state of the table. So like I said, we don't need to update the ones in white, we only have to look at the ones in red. Okay. So this whole algorithm is just taking averages, like we already did with B and C. So to get the distance between A and B and C, it's just going to be the average of A to B and A to C. So the distance between A to B is 10, the distance between A to C is 12, and when we merge them into one column, it's just the average of 10 and 12. So that's 11. So that's one of the 3 numbers we have to come up with to fill out this diagonal, or above this diagonal. So is there any confusion on how we got the updated distance between A and then the new pair B and C? Okay. I mean, if you have the distance between A and B and the distance between A and C, then for this algorithm, the new distance is just the distance, the average distance. I don't know why that's, sorry. Okay. So we did that for one of the 3, now we can do it for the second of the 3. So the distance between B and C and D is going to be the average of the distance between B and D and C and D. So on the original table, we can look at the distance between B and D, which is 4, and the distance between C and D, which is 6. So if we just take the average of those 2 and put it in the blue slot, then it's 5. So 4 plus 6 divided by 2, that's 5. Okay? And then finally, we have E, which is kind of like our outgroup, and we need the distance between B and E and C and E. So it's the average of 14 and 16. And so now we have another diagonal, or a filled-in matrix above a diagonal, and we have all the distances filled in now. So now we can take the next step, which is, now that we know the updated distances, we're going to pick the smallest one, re-update this table, and then update the tree as well. So let's do that. So up until this point, Does this stuff kind of make sense? It's, you take a pair, merge the pair together, and then take the distances between that pair and everything else. All right, so now this is like the next loop of the algorithm. We're on like step 2 now. So now we have a new matrix that we look at. We pick the smallest one, which is 5. 5 relates to the most recent common ancestor between B and C, paired up with D. So the D is the closest thing to both B and C in this scenario. So, like I say here, we updated the matrix. We picked the newest, lowest cluster. It's going to be 5. 5 divided by 2 is 2.5. So the distance between all 3 of them, B, C, and D, is 2.5 from D. But because we have to consider how far away BC was from B and C, we know that it's already 2 away. So the distance between B and C's most recent common ancestor and B, C, and D's most recent common ancestor is 0.5. So if you're like kind of put this in English, it's the split between the B and C branch and the D branch was all pretty close together. So all these kind of split off at a very similar time, is what that's saying. Okay, so because B, C, and D, most recent common ancestor, has to be equidistant to B, C, and D, that just means it's 2.5 distances away from D, it's 2.5 distances away from C, and it's 2.5 distances away from B. So now the most recent common ancestor is just the midpoint of B, C, and D. Did that? Yes?
I guess I'm just confused. If I look at the original matrix, I would think that the distance between B and D has to be the same between, as between B and C.
It's
but
because
in this final point, thing, it doesn't look like that.
Yeah, you're right, because we're constrained by the fact that it has to have 2 branches coming out of it. And we're also constrained by the assumption that these are all equally distant from each other, because it's like the molecular clock idea. But in practice, that's not what happens. So that's why the numbers don't kind of add up when you look at the tree.
So if you had randomly selected B and D first, then the tree would just look different.
Yeah, it would look different, but I mean, I don't think it can represent that B is the same distance from C and D based on only picking a pair of things. Yeah, it's because it has to only have branches with 2 things coming out of it, and also because our assumptions are not biological assumptions. Yes?
Is it ever possible for the distance between 2 clusters? Like, I know it's not the case for this example, but for example, in another example, could distance between BCD and BC be 0, and then BC and D would, and then those 2 clusters would just kind of merge into MRCA from which B, C, and D simultaneously came from?
I don't think these can... Yeah, I think even if you start with a 0, you're still going to be averaging something higher than 0, so it always becomes above 0 at some point anyways. Because you can't average 2 numbers above 0 and get it to be 0. And if you average 0 with a number above 0, it's also going to be above 0. So at some point, the distances do start spreading out. But for class examples, let's not think about things that are the same exact species, which would be 0 difference. We assume that enough time has passed for mutations to accumulate between species, and that's how we define species. Yes?
In the lecture, he didn't divide the gene distance by 2. He just put them the number, I guess, so they put smallest one is 2, and he just put 2 right there.
Yeah,
Is there a difference, or it's just the same, I guess, sort of?
I'm not in charge of the lecture slides, so I'm in charge of the homework and grading the homework, and I'm in charge of the discussion. So if I'm in charge of all these things, then just do it this way. But I mean, when you make the trees and you use the actual tools for the next parts of the homework, it follows this algorithm. It splits it by 2. That's the proper way to do it. Yeah, I don't know what's going on in the slides. So, sorry. Okay. So now we have 3 species represented by a most recent common ancestor. There's still 2 more species, A and E, left. So if we just keep going through the algorithm, the distance between A and E didn't change, so it's still 7. So we don't have to update that. But now we have to find the distance between A and B, C, and D, and then B, C, and D, and E, which are the last 2 pairs remaining. So those are marked in red. And then if we want to find the first one, we say that the distance between A and B, C, and D is just the average of the original distance of A between A and B, A and C, and A and B. So the average of all the orange squares is 10 plus 12 plus 8 divided by 3, and that's 10. So again, the midpoint of A and then B, C, and D is the average of A to B, A to C, and A to D. This is just kind of the next round of updating the table. So we found that one. Let's do it for E. So the distance between E and B, C, and D are just the pairs D to E, C to E, and D to E. So now the average of these orange squares, that's 14. Because 14 plus 16 plus 12 divided by 3 is 14. And now we have an updated matrix that we can just pick the minimum distance. So on this matrix, we did all this work to compute the distance between A and B, C, and D, and E and B, C, and D. But it turns out the closest distance was just A and E. So all that work is still going to be useful in a second. But we select that the next closest pairs are A and E, and they're separated by 7. So again, 7 divided by 2 is 3.5. We want the most recent common ancestor between A and E to be 3.5 away from its midpoint, which is the node AE. So again, just like we did for B and C, it's 3.5 away from A to the most recent common ancestor and 3.5 away from E to the most recent common ancestor. So that's kind of something we've already done before. But now the tricky part is connecting the most recent common ancestor of B, C, and D with the most recent common ancestor of A and E. So we'll do that. And there's only really one possible selection we can do, so we have to calculate these distances. So now we know that there's only one left, and it should be the midpoint to all of them, so we're going to call this the root node. We don't have to name it A, B, C, D, E. We can just say the root node is going to be the next one we put on the tree. Any confusions up to this point? Yes?
I guess my question is, when we combine, for example, BC into one node and update the matrix, do they calculate the next one's neighborhood that matrix?
You always look back to the original one. You can do it between each step, but you have to consider that the number of nodes change between each. You're always adding one node, so sometimes it's like divided by 2, and then the next one's divided by 3. Or it's better to just only look at the midpoints between the original matrix.
Yeah, that's my question is, because I thought the whole idea is for each round we combine the nodes into one.
It's looking for the midpoint of all leaf nodes in the cluster. So if you only have the midpoints of 2, you can't just average those 2. You have to look at all the leaf nodes again. I'll show you I'll show you.
Yeah.
Okay. So to fill this in, now we have 6 nodes that are included in this cluster, and we want the midpoint of all 6 of them. So we want the midpoint of pairs AB, AC, and AD, because that's the first half of AE goes to BCD. And then we want E between B and E, C and E, and D and E. So it's just kind of how the algorithm is constructed. So you look at all the pairs of the nodes in this cluster, and you calculate the average of those. I mean, you can come up with other ways to make trees like this, but it wouldn't be like the algorithm that we're using for the homework. So if we look at the average of 10, 12, and 8, and 14, 16, and 12, the average ends up just being 12, because it's all those divided by 6. And then how does this look on the tree? Well, the 12 divided by 2 is 6. So 6 should be on this side between each leaf node, and 6 should be on this side between each leaf node. So 6 minus 3.5 is 2.5. That's the distance between the root and the most recent common ancestor. And then the root on this side, the next most recent common ancestor is 2.5 distance coming out of it. So you need to just say 6 minus 2.5 equals 3.5. And so in this case, the distance from the root to A is 6, the root to B is 6, the root to C is 6, the root to D is 6, the root to E is also 6. So now that's the UPGMA algorithm for making trees. And like we saw, it does make some assumptions, and it's not perfect because from this tree, it doesn't come out to be this matrix when you traverse the tree. But that's just like kind of the heuristic for building these types of trees. There's better ways to do it, but they're more mathematically complicated. And this is a real simple one, so it's a good example to just kind of work through on the homework, because you're really doing just the same thing at each step, and then just adding stuff onto the tree at each step. Okay, so yeah, that's all I'm going to talk about for question number 1 on the homework. Are there any more questions? Yes.
Should we just show a like an upgraded matrix that we show our for computation, right?
Yeah. So when it says show your computation, I want to see this matrix. I want to see this one filled in. This is like the step before. I want to see the step before that, which is this one filled in. And I also want to see the final tree, which is this, with all the numbers and everything on it. Okay. Any more questions on UPGMA? Okay. Oh, yes.
So you calculated the root nodes by looking at 6 different leaves.
Correct.
Is it just coincidence that it's the same if you were to do it distance from A to BCD is 10, and the distance from E to BCD is 14, divided by 2 is 12?
That's just because mathematically it comes out to that. I mean, they're equivalent in that case, but when you have the 3 nodes, you can't just divide it by 2 because there's like halves involved. So the average of an average with like even numbers, you can simplify it to just being an average of averages. But when you have an odd number, you can't just say an average of the number and the average is not going to be the average of the 3. So it works out because there's even number of nodes in this example. Okay. We can always come back to this, but we're about halfway through class, so I'm going to talk about the next one. We ask you about short internal branches, and we say they're less reliable than longer branches. So what does short mean? Short is just, you can kind of do it by eye. They're kind of the mini branches. What does internal mean? Internal means it's not from a root node to the direct most recent common ancestor. So that's not an internal node. That's not internal. From mouse to this one, that's not internal. Chicken, this one's not internal. But anything between most recent common ancestors, this guy, that guy, that guy, that guy, that guy, that guy. Those are internal nodes. If it touches a leaf node or a node with a name on it, it's not an internal node. So in this case, the short internal ones would be the ones between mouse and then rabbit and human. So the English kind of translation of that is you're saying the split between mouse, rabbit, and human is kind of so close together that you don't trust your two branches coming out of them to be biologically accurate. There might be some noise. Maybe it's hard to. Maybe rabbits split off from mice after humans, and these two things split off. You don't really know the order when there's such a small internal node. That's what they're kind of getting at there. So in the tree that we just created from the video I sent out, there's a short internal node of about 0.5, and that's because if we look, you can see the distance from B to C and the distance from B to D was both 4. And it's just really short because we had to pick one instead of considering they all split off at the same time. I think that's all I have for that comment. These trees are good for the computer because computers think in terms of like ones and zeros. So when you have a split, that's only 2 options. But when you have 3 things combined, like if it's split off into 3 separate nodes, the computer, those algorithms are a lot harder for the computer to do. So these types of trees, they're pretty much, they're biological because the split can only happen at one point. You can't have one gene change and then 3 separate species come out of it, if that makes any sense. But the noise involved complicates things when we think of these sorts of trees. Okay, that's all I'm going to say about that. Any questions on the rest of the homework in the last 20 minutes we have? Well, I'll stick around this whole time. Yes?
3B.
3B. Let me get the homework out.
So they asked like the molecular clock assumption issue.
Yeah.
Don't we have to look at the sequence of the individual organism in order to see like if like to see the sequence like how much they're different? Because they don't tell us like anything about like they just give us the length and if I look at the image that it generated, it seems to show like doesn't show any like how similar they are.
Mm-hmm. Yeah. So with these trees, the distances are kind of reflective of how similar the sequences are. So the idea behind molecular clock is that you can pick a point on this tree that is equidistant to every other point on the tree. And if your tree comes out that that's not the case, then that's the answer to the question. So something that breaks molecular clock would be so this is a branch between rabbit and human, but if molecular clock was broken, human would be like way out in the corner. And that would imply that given the same amount of time, humans had way more time to evolve than rabbits did. Which, I mean, biologically, rabbits have a quicker lifespan and they're doing it more. But, yeah, molecular clock says that anytime there's a speciation, they both branch out at the same speed. So if you see it's something that doesn't line up with that, that's something that's breaking molecular clock.
Okay.
Yes?
I think the professor said something about the MRCA could be anywhere along the lines connecting rabbit and human. So like
That's a good question for his office hours, but I think,
yeah,
you're right.
Yeah. So then,
Because it's an unrooted tree.
right. So then I was confused. I guess I haven't thought it through. But even if human were way out there, couldn't the MRCA still be at a place where they're equidistant from each other? You know what I mean?
Yeah, you could have that. but then you have to look at the ratios of the other nodes, and chances are they're not going to come out to be the same.
Like what do you mean ratios?
You're right. There has to be two mismatched branches for you to not be able to pick a point.
That's for the MRCA of the whole tree, right?
Correct.
All of it.
Yeah. I don't know if he wrote it on the board or if it was in the slides.
I think it was kind of like pointing to it.
Yeah, I don't think it's in here.
So I guess I remember him saying if you can't find a spot where that's equidistant from every sequence, then it's not under the molecular clock.
Correct. So in this case,
Right.
you can pick a point. Well, if you pick a point somewhere on this line, then chimp and human are going to be further away than gorilla is going to be. Because gorilla is always going to be closer to macaque than it is chimp and human. This is hard to see.
So you can tell that much just by the splitting.
Mm-hmm. Yeah, so I guess you kind of have to just like either calculate the distances or kind of think it through, but like if you pick a point here, it has a chance of being equidistant to all three things, but then macaque is way further out. And if you pick something on this line, just because of this line, the chimp and human are going to be further away, no matter where you pick a point on this line.
So this is an example of not
Correct.
MCA.
Yeah. And I mean,
Did you have an example of MCA with an unrooted tree?
did I? I did
Or
not.
did he? I forget.
I don't know if he did it on the board or if he did it in class.
If the macaque is just as far away as the gorilla, if that length is the same, look at that.
Correct. Yeah. Was that what you were asking, or were you asking for where the root would be?
What did you just say?
So, like, imagine you made the line to macaque the same length as around the gorilla, then that would be a unrooted tree, but the MCA is still.
Yeah, it depends on where you put your root, is the answer.
And, it says, last question.
Yeah.
It says the two rooted trees above correspond to that same unrooted tree. Okay. Are those two rooted trees MCA? Or no, because they're all not quite the same.
I mean, I can't imagine they would be just because of this. Stuff.
Okay.
Yeah, you can make trees, but they don't follow molecular clock. Like the next algorithm that we kind of skip over is neighbor joining, and that doesn't consider molecular clock, I don't believe. So these are good questions, and they're kind of getting outside the range of the stuff we want to talk about for the homework. So if you have these types of questions, go to his discussion and ask him. Did that answer your question about molecular clock? Okay. So any other homework questions?
Yeah, I
Yeah.
get how to like specify the location of like the root.
Yeah, just put an arrow or put a star or put a circle. As long as I can understand what you're annotating, then it's fine. Like here, we say rooted tree, and he puts a little star on where the root would be.
Okay.
Yeah, that's fine. If you want to like color this node red or something, that's also fine. I could have done that on the PowerPoint. Anyways, yeah, as long as I can tell what's going on, then it's fine.
Okay, so we don't have like list sequences and 7 3 or whatever it was talking about. Question 2B.
I think that's what the question's asking. List the sequences. That's just a way of specifying the node.
Yeah, but in the question we give you the sequences and we ask where the root is.
Yes, that's what I was.
Yeah, so just put like a little star or a little arrow or a little circle or something. That'll be the right answer.
That says uniquely specify how the root splits up the tree by simply taking the smaller of its two subtrees and listing the sequences in the subtree. So, oh, the sliders principle specify the location of the root. So yeah, can't you just list the sequences of the smaller subtree?
I mean, if you're looking at the root of the whole tree, you would just list out all the sequences, and that's not very useful.
You just list out.
Look, I'm going to grade the homework based on the fact that I want to see a tree and a little star somewhere on the... So in 2A it says make a tree, and then in 2B it just says point to the root of the whole tree, and then in 2C it says point to the root of the branch containing these 4 guys, these 5 guys. That's how I'm going to be grading it, so just do it that way. Yes?
I just have a question about like 2A.
Yeah.
There's this part where like after you, I don't know, like you put in the like whatever dot like stroke distance, like you create the file name.
Yes.
Then like in the code in the homework it says like N and then Y. But
Yeah.
this screen that's coming up on my like it's asking me like are these settings right? There is no N. So if I put in N it just says error. And like I can type just the yes, like from the beginning, just Y, which is like all of them are correct. So I don't understand what that's trying to tell me to do.
So I think you might have been looking at the wrong part, because the first one you just type in the name of the file and then type yes. So there is no N in Philip Probe distance.
Oh, and then at
The next one there is an option for N, and that's how you tell it you want to do the UPGMA algorithm.
okay.
I did the same mistake, so no worries.
Sorry.
Program are we running this on?
It's the Linux operating system, and then you're running the program called Philip. Yeah. 1 second. So this is the output, and then N just says, do you want to use neighbor joining or UPGMA?
And you want to use UPGMA.
Yeah. So when you type N, it flips. Because right now it says neighbor joining is what you're going to use, and then now it says we're using UPGMA.
And then you did yes.
Yeah. Okay. Any more programming questions like this, or actually, what's your question?
Well, I have a question for B.
4B.
Yeah, so I opened up the file and I don't really know exactly what I'm supposed to do.
Okay, this is the consensus tree, correct?
Yeah. So I know.
So you're talking about the text file, right?
Yeah. Is it? Yeah, that.
Okay. So you know how I listed the pairs in like the parentheses, and then it was like the pair AB in parentheses on the slides? Okay. Yeah, so I was using like this notation where the pair between AE and BCD, that's like one pair of things. So in this view, it also has these parentheses where it has, there's one leaf node, another leaf node, and then it has the distance between them. So it's pretty much what I showed in the PowerPoint, but now it has a distance involved too. So it's kind of confusing in the early ones because the distance between everything to itself is 100, but then the distance between these two and then the next thing up on the branch is 98. And since this is a consensus, that's 98% confidence. So did that kind of make sense, first of all?
Like, yeah. Like, how do you interpret the last one? Where there's like a pair and there's like four numbers?
What are you talking about here?
Yeah, like when you're looking at Z flag C, like
Yeah.
after the initial parentheses, there's like 100 and then 91, 97.
Okay. So between Z flag C and flag C, they're both 100% to each other. They're 100% confident that this branch is coming out of DU, which is the next parenthesis over. They're like recursive parentheses, kind of. So if it was our original tree, it would be A and B. The only thing this is adding is like the confidence. So let's say we're 100% confident. And then the other parentheses are like this node, comma, and then C. And we also need to have like a confidence. Let's say we're only 90% confident with this branch. So there's like recursive parentheses going on. So then the branch between the most recent common ancestor between A, B, and C, and then D, we can also give a confidence to. So I don't know, 60% confident. That's this is like they call it like Philip notation or something. Do you want me to send out a link for reading this tree format? Okay, I'll write that down. Okay, so this text file had like kind of the same order, or that's not true. But this text file before we were talking about confidences, it would represent the distances between pairs, and now it represents how confident you are of these branches. So at this point in the homework, this is a consensus tree. We're just telling us how confident we are between stuff. So if this is the tree view of the consensus tree, we can see that shorter lengths are less confident branches. So around this area, we're less confident which branch kind of came first. Was it these guys evolved first or these guys evolved first? We kind of don't know. So for the consensus tree, the length is how confident you are of the branch coming out of it. But for the other trees, like we did in the PowerPoint, it's the raw distance. That's what those numbers mean. So here, these are evolutionary distances, and then in the consensus, it's like confidence of how sure you are that these branches are where they should be. I'll let that sink in, and then any more questions afterwards? I think we got 5 minutes left. Okay, well, I'll stick around for 5 minutes. I'll be